All right, we're on page 6 in your packet. Yesterday you guys had made your intervals, and so we'll check those in a little bit. Let's just go ahead and get this done. Make sure we have enough time for this, because I want to make sure we have enough discussion time for um, the things that affect the size of the intervals. So that's what we're going for. Now we're interested in what changes the size of the intervals, because as a researcher, you have the ability to change two things, and then you can change the size of that interval. What do you think is better, a smaller interval or a bigger interval? If it's an estimate of something, it's an estimate, and a smaller one is better. Because if I tell you something is between 5 and 8%, that's better than saying it's between 5 and 25%. Good. So a smaller interval is better. So we need to know, how can we make it smaller and what changes it? All right, so here we go. So let's discuss the values that change the size of the interval. We have to first look at the formula, which we know. Let's review. This is our p hat plus or minus our critical value. What changes the size of that critical value? What does somebody tell you that changes the size of that critical value? Yes, the confidence level. So somebody will say, I want you to be 90% confident or 95% confident. So how confident you are to be is what changes that Z star, that critical value. And then standard deviation. Now, you know that this standard deviation, you're well aware. Good. Okay. Now, you do not have control over p hat. You get what you get, and you don't throw a fit. That's right. When you do your proportions of throwing your globes around, you got your proportion, and we didn't dispute that. That's what you got. So p hat cannot change. So tell me, when I'm looking then here at this formula, what things can change that you could, as a researcher, change the size of? Oh, perfect. Sample size is one thing that you have control over. Good. What else do you have control over? How confident you want to be. Okay, so those are the two things. How confident you want to be and your sample size that will affect the size of our interval. All right, so let's go ahead and go forth with this. The first thing is we want to identify the margin of error. Remember, that's those whiskers. Remember when we made our little intervals over there on the board? That was the place that you had. That was your p hat, and that's what you got. And then you went your margin of error up and your margin of error down. So you went your positive margin of error up and your negative margin of error down. So those things that are plus minus, that is this section here. So the part after the plus minus is called the margin of error. Okay, that's those whiskers. How much go up, how much go down, that makes that interval, that spread of an interval. Okay. By the way, this value right here is the upper value in your interval. You know, remember that? In your interval. And then, of course, this one down here is your what? Good. That's your lower value of your interval. Okay, very good. So let's move on. The following affect the size of the confidence interval. You told me this earlier. Critical value and the standard deviation. Okay, so more specifically, me telling you how confident you are to be. So confidence level affects your critical value. What letter do we represent critical value with? Z star. Very good. So our Z star. Okay, so let's do some little examples of that so we can see how it changes our interval. So let's do 3 little examples. Draw yourself 3 little normal model sketches. Do you have those drawn there? No, you don't. Okay. I thought I might have drawn them there for you. Give yourself 3 little normal models. Okay? And do you see how I draw the lines and they get wider as I go down? Okay, those little lines are getting further apart as I go down. So I want to have 70% confidence in this first one. If I have 70% confidence, how much is left in the tails? 30 total, which makes 15 on each side. Very good. So in that case, this critical value for this problem is created from what computing? Inverse norm of the area below. Is the z at that spot? So inverse norm of 0.015, that's wrong, of 0.15, yep, sorry, my bad, is 1.04. Okay, so that means that spot is 1.04 standard deviations down. Okay, all right, let's do the next one. Let's say it's 80% in the middle. So do you see how it's wider? Because it's 80%. 20% is left in the tails, which puts 10% in one of them. So it is. So my inverse norm of 0.10 is 1.28. So, what do you notice about this? 70% confidence to 80% confidence, and my critical values went from 1.04 to 1.28. What's happening to my critical values? They're getting bigger because I'm getting farther away from the center. Okay, let's do one more. Let's do 90%, and then we know what's in each tail. A 5%. So does anybody recall inverse norm of 0.05? 1.64, good. Okay, so in summary, look at this little picture I drew over here for you. As the confidence level, or your Z star, as your confidence level gets bigger, what is happening to this margin of error? It's also getting bigger. Okay, so in summary, the conclusion of the change is as your confidence or your critical value goes up, it's an up arrow, then your margin of error. And if your margin of error is getting bigger, what's your interval size doing? No. Yeah, remember your margin of error are your whiskers, so if your whiskers are getting bigger, what's your interval doing? It's getting bigger. Okay, so those go together. All right, so there you go. There's our summary. Now, hey, let's talk about one thing just real quick. Do you notice that this margin of error is made up of two things that multiply together? So a margin of error is made up of a critical value and the standard deviation. So if I have two things that multiply together, if one of them gets bigger, what will happen to the product of those two items? It gets bigger, yes. So you have to keep that in mind as we're going along through these. And if one of them gets smaller, then what happens to the product of those two items? It gets smaller, okay? So this is all built off of that today. All right, so let's come down here and examine standard deviation of the statistic. Now, this is all based off the fact that this standard deviation of our p-hats is based off of this formula here. Okay, and again, what in that did we say we have control over? N. Can we control p-hat? No, because we get what we get and we don't throw a fit. So we know we've got that going on. So let's do some computing here and see what's happening. All right, so so we know that N is our sample size. Okay, and that's what really is affecting our standard deviation. Okay, so let's do some math. Let me just go ahead and set the p-hat just for this problem. Let me just say you got 50%. Okay, I know we had a group that got 50% when they did their globe toss. Okay, so let's just say you got 50%, and we're going to go with that. So let's look. The standard deviation if sample size is 50. Let's see what that equals. So that's 0.5 times 0.5 over 50. I computed that already. That number is 0.005. 0. Oh, I don't know about, hold on. Because I'm seeing, oh, yeah. Never mind. Nope, that's good. It's all good. It's what I expected it to. Okay, so I went into my calculator and I typed the square root of 0.5 times 0.5 divided by 50. And I got 0.07. Yeah, and what is 1 minus 0.5? Ta-da! 0.5. Okay? Yeah, so I just didn't type 1 minus, I just put what it was. All right. Hey, let's do this again with a sample size of 100. Anybody want to guess what's going to happen? Nope, you do not. What do you, here's what I want you to guess. What do you think? Do you think this number is going to be bigger or smaller than the previous standard deviation? Well, our sample size got bigger. That number is 0.0, drum roll please, 5. It is. So, as n got bigger, our standard deviation got smaller. And you know what though? We've experienced that before. Let me explain. Do you recall whenever we had this and then we had this? We have our normal model, and what happens whenever our sample size went up? This would be like if sample sizes of 5, sample sizes of 50. What is going on? It's getting closer to the center. Good. So closer to the center, less varied. If it's less varied, what is another key thing for that? Smaller what? Yep, smaller standard deviation. No, this is just a discussion. We've already seen this. As we have bigger samples, we have smaller standard deviations, and that summarizes this right here. Down here. Got it. So as the sample size went up, what did that first change? That changed the what? Sample size going up, good. Changes the standard deviation. And it makes the standard deviation go what? Smaller. You are less varied. Okay, good. Now my question is, how does that affect the whiskers of our... Well, let's look. Here is our formula. If this number gets smaller, what's going to happen to this product? It gets smaller. So if standard deviation gets smaller, our product gets smaller, our whisker gets smaller, so the interval gets, so the margin of error is getting smaller. All right, so that is the big, huge idea that you have got to know very well and near and dear to your heart. I have got a computer visualization of that, so let's discuss that now. Okay, here we go. So I've got this picture here, over here on the left, and I've got these particular, this thing I am moving is the confidence level, okay? And this bottom one is the sample size. So I'm going to set the sample size at 50. Okay, you ready? Here we go. I'm at 80% confident. 80% confident. You see this picture? The green is the whole interval. This little purple is the margin of error up. Okay, so here I go. Confidence level is going to go up. What's going to happen to the interval? It's going to get wider. So here we go. Drum roll, please. Okay, there it goes. So as margin of error goes up, the interval gets wider. Okay? All right. Now let me put this back down to 80, or I'll just leave it at, say, 90 or so. Okay. Now let's talk sample size. Currently, I have the sample size at 50. What's going to happen as I go up on my sample size? Up on sample size gives us a better estimate. So what's that going up on sample size going to do? Make the interval do what? Smaller. Because isn't bigger sample size going to give you a better representation? Okay, so that allows you to pinpoint the answer better. So, sample size. So as your sample size goes up, your margin of error and your interval is getting smaller and pinpointing closer around the true answer. Okay. That estimate is your p-hat. Wherever you got your p-hat, that's your thing. Yeah, just wherever it starts. Okay. All right. So there was a visualization. So let's go ahead then and move on to the next page in our notes, which we've got an example here. Let's see. In the middle of the week. You can look at the calendar in the front of your packet. I don't know. I haven't been able to put the calendar up on the board yet. Okay, here we go. All right. So Presidential Pete is in the home stretch of his campaign, and he wants to know if the polls predict that he will win the election. In a recent poll of 1,020 randomly selected voters, which, do you know, by the way, the Gallup polls, they go by, they will call people until they get 1,000 responses, okay, or in that vicinity of 1,000 responses. So this is a very valid amount. That's generally what they go for. Ah, there we go. That's what they go for to get a good estimate. Okay, they found that 484 responded in favor of Presidential Pete. Construct a 95% confidence interval for the true proportion of voters who would vote for Presidential Pete. So we're going to do that shortly. But let's first answer this question. What happens if you raise the confidence level to 98% and instead of being at 95%? What's going to happen? Okay. So hey, let's always do this if we have to think about how things change. Okay? All right. So the margin of error is that critical value times the standard deviation. Okay, that's always the case. So let's see. If I go from 95% to 98%, what is changing in my formula? The Z. Yeah, the confidence level. And what in my formula, what mathematically does that change? Okay, so you raise the confidence. Raising the confidence raises what number?
The margin of error.
No, well, which of these things change? The Z, thank you, the critical value. So the critical value, thank you, is going up. So now what is going to happen to the interval? Now the margin of error goes up, so the interval gets wider. Yep, gets wider. Okay, very good. Here we go. Pete wants another poll to be taken, but only has enough campaign money for 500 voters instead of the previous 1,020. What is changing in that case? No, p-hat's not changing. Good. The sample size went from 1,020 to 500, so it went what? Down. Okay. Is that a good thing to go down on sample size? What's that going to make you be? Less accurate. Sample size going down makes you be less accurate. So what of this formula up here does that change? Standard deviation will do what? It's less accurate, so standard deviation is going to get bigger and wider. Okay? Less accurate means bigger and wider standard deviation. So that's going to go up. All right. So then what will that happen? What will that do to our interval then? Or it'll make our margin of error get what? I don't think so. I think this standard deviation is going up. So it goes up. So therefore, again, our interval gets wider. Okay. So we'll practice those more, but I'm telling you guys that I think the key to being able to understand what's happening is to use this right here and see what's happening to those numbers. Okay, so next item, let's go ahead and we're going to learn we're going to do a full, let me show you where we're headed with this. On the next page, there's this little chart, okay? This is making a whole entire interval, but we have to do it where we define like what it is we're finding, then go compute the interval, and then make a concluding statement. So we have to make a very well thought out answer that is in context. So therefore, I need to teach you what this thing called parameter of interest is. So that's what we're going to learn first. That's about the only thing you don't know in this process, so let's learn what that is. First, let's practice defining a parameter. We're going to use these all the rest of the year. A parameter, yes, a parameter is a letter that is about the entire population, like P is the proportion of whatever for the whole population, okay? Or, so that's what we're going to be doing for a while, or when we get to means, it'll be a mu for the population mean. We want to make sure that these statements are out of the correct population, so we make sure we define the population that we are talking about. Make sure that these statements have to be in present tense or even future tense. You cannot tell me, you cannot make an inference about something that's happened in the past. Why can I not infer about what's happened in the past? Because it already happened. Thank you. I'm going to use a sample and infer about current situation or the future. All right, so we're going to practice this, and I'm going to guide you through a few of these. So here we go. Example 1. In 2006, 16.1% of all heart attack patients died from any cause in the first 30 days after being admitted to the hospital. There has been recent national effort since then to improve the quality of heart attack care at hospitals. Have those efforts improved the heart attack death rate for any cause in the first 30 days after being admitted to the hospital? First, is this a mean problem or a proportion problem? Proportion. Yes, it is a proportion problem. So we're going to write P equals. Okay. No, we're going to infer to what population? What are we going to make a statement about? Who is it that we're making a statement about?
Heart attack patients.
Heart attack patients, and what about them?
They're dead.
The proportion of them that
Die
die
from the first cause.
for any cause in the first 30 days. Good. So guess what? It's going to kind of follow this, but there is something really tricky that I heard y'all say wrong. It is not about, so this will always start out with the word proportion. Proportion of heart attack patients that do what?
Die from any cause.
Oh, die. Present tense, not died. That's done. That has happened. That die. We are talking about what is the current rate of death for those heart attack patients that die from any cause in the ... I'm just going to leave it right there for now so we can go on. In the first 30 days after being admitted to the hospital, okay? When we actually do the full test, we'll write it all in, but we're just getting an idea what's going on. Or the full assignment. Okay, here we go. Example number 2. Let's see what this problem's about. A team of eye surgeons has developed a new technique for risky eye operation to restore the sight of people blinded by a particular disease. Okay? Under the old method, it is known that only 30% of the patients who undergo this operation recover their sight. Only 30% of those kinds of patients recover that. And so then we'll later talk about, can we justify that this new method is better than the old one? But so what is this problem about? Yeah, people that are blinded by a certain disease, and then they're going to do, what are they going to do? And we want to see if it makes them better. Yes. Okay, they do the new method. So how are we going to start this? Is this a proportion problem or a mean problem?
Proportion.
How do you know?
The percentage.
Because it talks about 30% of them. Okay, so P equals, and what's the first word I'm going to write?
Proportion.
Okay, so it's the proportion of what?
I person.
I think it's people blinded by a certain disease. People blinded by a certain disease that do something here in a second. We'll write that. People blinded by this disease that they're talking about. Okay. Proportion of people blinded by this disease who do what? Who, what are they going to do so we can see if it's better? Yeah, so who undergo the new operation, the new procedure. We'll just call it procedure or operation, whatever. Yeah, the new operation method. Okay, yes. And what do they do? And we want to know the proportion of them that get their sight back and recover their sight. We want to see what proportion got better under this new method. Okay, what proportion got better under this new method? So see, there's lots of things going on here. Yes, ma'am.
I'm just kidding.
So lots of things going on here. All right, let's try one more. All right, example 3 before we go on to our problem. Here we go. In 1990, 86.3% of the population of Cortland, New York was composed of New York State natives. Has the percentage of native New Yorkers changed since 1990?
Proportion problem.
So it is a proportion problem, okay? So here we go. P equals, and what's my first word?
Proportion.
Good. Proportion of what?
New York State native.
Proportion of Cortland, New York that are New York State natives. Yes. Proportion of Cortland, New York residences. New York residences that are New York State natives. We can't chintz out on all this writing because there's lots of details in there, and it's meaningful. It's meaningful to what it is that we're going to make a conclusion about. All right, so let's go back to this problem here. This Presidential Pete one. Here it was again. Let's remember, Presidential Pete is on the home stretch, and he wants to know if the polls predict that he will win the election, and then we have some information there. So what is this, a proportion problem or a mean problem? Okay, hint, this whole unit that we're doing for a while is proportions. We're going to go through all proportions first, and then later we'll do some means. Okay, so we're going to be doing proportions for a while. All right, so what is the parameter? What is this problem about? Yep, who do what? Who vote for Presidential Pete. Very good. So how do I start this? P equals. Good. Proportion of voters who vote. See, that's a present tense. Who vote for Presidential Pete. Well, I think if they vote for him, that's yes. No, I'm not just saying they vote, period. I'm saying they vote for Presidential Pete. Okay, so now we're going to get to the math that you guys have practiced the last 2 days. Okay, here we go. What's in? All right, 1020. P hat. What's P hat? 484 is not a proportion. Nope. That's a confidence level. 484.
We're trying to find.
What? Perfect. 484 over 1020. Okay. Oops, sorry. So 484 over 1020, and I've got these numbers here. Let me pull that up real quick. 0.47. So our p hat is 0.47. All right, now z star. And if you tell me 0.95, I'm going to have to hurt you. Okay, so remember here, if you need a visual aid, here's a little quick visual. 95% is in here, so how much is in each tail? 0.025. So my critical value is inverse norm of 0.025. So that's 1.96. Okay. All right, moving along. Standard deviation of p hat. How's that? 0.47 times, what's the 1 minus that? Good, 0.53 over 1020. And that is 0.016. Okay? All right, so there's all the facts. Let's now go make our interval. I wrote the formula up here for you. What is this statistic? Okay, that's your p hat, and our p hat is 0.47 plus or minus. This critical value is z star, and we said that is 1.96. This standard deviation is 0.016. So what do I do first according to the order of operations? Multiply 1.96 times 0.016 and you get 0.031. Then we can add to get the top one and subtract to get the bottom one. And like I said, we're going to check those ones that you did yesterday here in just a minute. So there's our interval. I put this 0.501. I went ahead and put that on there. Why do you think I would do that in this election result? It could be a little bit above 50%. According to this, he could win. Okay. All right, so our conclusion statement. How does our conclusion statement start? I am 95% confident that the, what? Good. True proportion. And then this comes straight up from your thing that you wrote up earlier. The true proportion of voters who vote for Presidential Pete. Okay? So that's always going to come straight from there. The true proportion of voters who vote for Presidential Pete is between 44% and 50.1%. Do you know if he will win or lose based on that interval? Do you know if he will win or lose? You do not. According to that interval, he could lose. According to that interval, he could win. So that's not conclusive evidence of him winning, by the way. Okay, so that's how that works. So that's the finish for that. Monday, we're going to practice doing some of those. But let's go ahead and check your papers from yesterday now.